Okay, space cadets, get ready for this. This is going to be fun. The corona is weirdly hot. Parker Solar Probe rules out one explanation. Nobody has been able to explain why the corona of the sun, which is way out here, is millions of degrees, and back here on the sun's surface it's only thousands of degrees. How did it get to be millions out here? Nobody can explain it. Well, we have a very similar situation here. On the surface it's about 100 degrees, but when you get out to our ionosphere, it comes up to almost 3,000 degrees. Again, no explanation whatsoever. Now, they thought it might have something to do with these S-shaped bends, which we're going to explain. I'll explain to you in a second. But they ruled that out. So let's see what they did find. This is Science Daily, your source for the latest research news. Okay, so certainly AI, artificial intelligence, can describe exactly what's going on with the solar corona versus the surface temperature. Why is it millions of degrees out here and only thousands here? Now, here's what they have to say. The sun's corona is hundreds of times hotter than the sun's surface, reaching temperatures up to 72 million degrees. The exact reason for the corona's high temperature is still a mystery, but some possible explanations include heat bombs, magnetic fields, nanoflares, solar tornadoes, and kinky oscillations. I don't know what to say. Everything is scrubbing through space. It's scrubbing on the particles that are trying to leave. And the same thing with us. It's nothing but ions out here. Let me show you what happens in space around bodies that are scrubbing through those particles. We have to scrub through them. Okay, so they've ruled those S shapes out because to heat the corona, the switchbacks need to move through the corona. They need to move through it. So learning where the switchbacks form is critical. Exactly. We want to learn exactly where they form, and why do they form there. It's critical for understanding their influence on the corona's temperature. They poured over the data from Parker Solar Probe's first 14 laps around the sun. The research team discovered that while the S-shaped bends are common in the solar wind near the sun, they are absent in the corona. They are down towards the sun, these S-shapes. We're going to look at that right now. You know, I've been showing the evidence of this for a long time. It's not my nature just to be critical for no reason, but I'm going to tell you, I'm critical of their abilities. This is just very common sense. We're scrubbing through the solar system. Let me show you. Okay, we are on an arm of a galaxy called the Milky Way, and we're being scrubbed through whatever's in front of us. We're being torn on the arm forward, which means that we have to push through whatever particles are there, and the sun does. They can see it streaming off of the sun. Well, and I will show you that as well, because during a solar eclipse you can see it very clearly. So we are being pulled through whatever's in front of us. That's what's causing the coronal heating. It's like scrubbing down the road. All right, let's just go over this one more time. We're on the arm of the galaxy, of spinning around, being dragged forward through whatever's in front of us. I don't know what's out there. You don't either. Now, what does it look like if we're in moving forward? Here's what it looks like. There it is right there. Now, the sun is literally pulling us. It has a ton of gravity because it's so big. It's pulling the planets behind it as we circle through the arm of the Milky Way. Now, so everybody spins around the sun. The sun is also spinning. I can also prove this. I can prove this without any doubt whatsoever. It's spewing radiation off the side of the sun because of the way it's impacting, and I will show you that. Everybody else has to spin through whatever debris is coming back. They call that the solar wind. And it's all the particles coming back from the sun as it goes forward. Now let's continue on. But don't forget, this is what we're dealing with here. and we are on the arm of the Milky Way. Now, there is an 11-year solar cycle, and I'm not sure whether it relates to these stripes or not. It could be related to something to do with this as we come forward through more and more dense space or less and less dense space, whatever, because it appears to be a charging of the sun, and then like a solar maximum and a solar minimum, and I believe that's all due to a charge up as it's spinning, basically almost identical to what happens with the light. I don't know if this is accurate or this is just some simulation, but they make it look like the electrons are flowing out into space, and sometimes they switch back, but sometimes they just continue off. It looks like there's vapor being given off by the sun. Now, that could very well be. Let me show you. But is this accurate, or is this just some representation? I don't know. All right, so I showed you this, and I say stuff is coming off just like the last thing I just showed you. Now, let's look at it a little closer as we're scrubbing through. What is actually coming off the sun? Can we actually see the particles? It turns out we can. And the reason is because the moon is in front of the sun, blocking the brilliance of the disk. And we can see just as if it was the sun, but we're not blinded. So we're seeing the light radiating from the sun. What can we detect from what we see? I go for the details. All right, now I can tell that this is a pole, and that's a pole, that's the center. Now it is spinning, and how do I know it's spinning? And how do I know it's spinning in that direction? Why isn't it spinning in this direction, Roger? Well, the reason is you see this red spot, that red spot, and that red spot. All right, let's come in a little closer. You see those? And you see those magnetic field lines around them? This is actual shot of the sun, you know, behind the moon. Now, that is extreme energetic and particles. There's a lot of particles there, a lot of particles there, a lot of particles there. Why? Why? And why don't we see that over here? Why is it only here and not here? Anytime you have poles, you know, North Pole and the South Pole, you have a spinning ball, a sphere. And that is what the Earth does, and the Sun does, and all spheres spin in space because they're scrubbing against particles. So they end up basically like rolling down the road as they bump into those particles. And that's what the sun is doing. All right, so the sun is spinning this direction, and everything's moving this way. So as it spins this way, the scrub zone mainly is right here, the center. You see the center? This is the poles, this is the center. It's scrubbing the most intently here. Now, what's that do? That sets up the biggest amount of magnetic scrub, and anytime you have an interaction between particles, you set up a field. It's just a field. That's what it is. And this is the main part of the field is right here. Well, what does that do? It pushes this field over to here and this field over to here. So you end up with these three regions, basically, as it spins this way. Now, it's always also going this way. And this is the trailing edge, just draping off. See how it's like trails off and trails off? It's like pushing this way. You can see that. Just think about it logically. We got intense scrub, we got a lot of magnetic interaction, but we got a ton of stuff flowing out of here. Every one of these lines is particles. Every time you see a glowing thing, it's some kind of particle. I don't care how big it is or how small it is. It's energy because a particle is interacting with other particles. Now, this is just sort of scrubbing off, but it's still a ton of stuff. This is really, really energetic. So that's my interpretation of the sun. There's the poles, sun spinning this direction, scrub, 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 trail, 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 move, 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 spin, spin, spin. That's what our sun does. And we all have to follow it. All right, my friends, can we make a representation of this scrubbing effect and why and where the borders are and so forth, to some similarity. And yes, we can, and here it is right here. So let's take a look at that. All right, you've always heard space is a vacuum. That's not true. It's not true at all. And they knew that. They've known about this forever. This goes back over 10 years. Empty space isn't empty. It says the foam on a head of root beer is a complicated environment, bubbles appearing and disappearing in a dizzying display of change. Empty space experiences similar activity with subatomic particles winking in and out of existence. That is light. Light is the subatomic particles winking in and out of existence. These subatomic particles are real and have a measurable impact on our universe because they are streaming everywhere through the universe, and everything that goes through it is being obstructed by them and slowing down. Light doesn't get stretched because the universe is expanding. Light is slowing down as it approaches us. That's what shifts it to the red. All right, stay with me on this. Don't forget, here we are swishing through the universe on one of these arms. Whatever's in front of us, we got to go through. Is there some cycle of 11 years that gets denser and less dense and so forth? I don't know. Is it this that the spinning charges up and then discharges? And I don't know. It could be either way in my estimation. Now, here is what is happening. So we are spinning through here. Now, here's the sun. Don't forget the sun is spinning. And it's radiating all kinds of particles. Now, most of them, let's say, are going to be light particles, which are subatomic. They're smaller than atoms. If you took an atom, you see how you got hydrogens out here, hydrogens and oxygens. The hydrogen is the smallest, basically stable atom. So they're the smallest ones. That's why they lift up off of the Earth's surface. The hydrogen, it doesn't have any weight to it. It just lifts off. Now, so it'll form our layers in the outside. Now, hydrogen, though, is not just one little particle. Hydrogen is 1,823 dipoles. You see these little minus charges all over the place? That's these. All right, when these big ones scrub against other ones, they lose particles. They lose these little particles against our particles. So you end up with a whole stream of particles around the Earth that's scrubbing around the stream of particles trying to get into the Earth, which is the light, and us scrubbing through those things. This is where you have an extreme amount of energy. And all you have out there is light particles, which is the negative part. Same thing with the sun. So out here on our surface is 100 degrees. Out here is almost 3,000. The sun is 10,000 or so on the surface, and it's millions out here. Same story. All that stuff trying to get away can't get away. It's scrubbing against everything out that's in space. And if you don't realize by now that there is a whole ton of stuff in space, then you're not thinking. And, now another thing is, I want to tell you something. Please don't argue there's no space, there's no this, there's no that. If you want that, that's fine. Just don't argue it here. It's just a dead-ended argument. It's annoying. I understand what I'm seeing here. I don't accept anything from anybody. Oh, you just accept this, you just accept this. No, I don't. I do not. I find NASA incompetent. I mean, what can you say? They can't understand this is the source of global warming. They can't understand this is the source of the corona. It's a scrub. They think that light doesn't slow down, and they're giving all these big measurements of how far everything is in space. No, it isn't. Light is slowing down as it comes through these fields. And everything we did was with almost no resources to speak of. This is with a cell phone, with some kind of app. And this is the fields that surround different things in space as they spin. When they spin, they create a field. It's like scrub, 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 scrub. That's basically what is causing these energy fields. And the faster it spins, there's a difference in the speed of the spin, how big the field is going to be, and all kinds of things create different spin speeds and vibrations that come out. But primarily it's charge, 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 discharge, charge, that type of thing. And that's the only thing I can take away from that in space. This is what's going on. Now, this one here, I believe, is Venus. Now, every polar particle, and everything there is polar. You see all these? These are all polar. This is polar. Everything is dipoles. There is nothing but dipoles. Now, when they spin in space, they create these fields. This has a double field. You see the big field here, and then they have another one right there, exactly the same. Well, now I say exactly the same. This is a secondary field running right up the same polarity. So Venus spins backwards and goes forwards. So it might have two fields. That's the only thing I can take away from this, because there's no reason you should have two fields. Now, everything we see in space is dipoles. It's just all dipoles. You see them? They have a bright spot and a black spot everywhere. And there's some strange things I cannot explain. I'm not even going to try. Now, on our Earth, we have the same situations we have on the sun. Here it's millions and 10,000. Here it's 100 and 3,000. Well, why do we have so much temperature change? And here it is. I can prove it. So I'm not making this up. This is where you get into really like low density space. There's a very, very, it's not like packed like on Earth where, you can spin windmills and so forth. You can pretty much drift through that, but you're going to bang into particles here and there. You're going to bang into other light. You're going to bang into dust. You're going to, all kinds of things. So you are going to slow down. No question whatsoever. You coming through all that stuff that's in space, you will slow down. Light slows down. So let's just get past that. And I've shown it in our experiments. Now, here is where we're spinning and scrubbing and moving forward, and we're interacting with the particles that are here, and we're scrubbing those particles away from these particles. And our particles aren't trying to get out into space. They won't go anywhere. They're being pushed in. So it's not like carbon is a cap on top of the heat. No, it's not that at all. It's that we are expanding because of burning carbon dioxide. Whenever you burn something that was just a stable little chunk of something that was in the ground, you bring it out and you burn it, it's like this. Before, you couldn't even see it. Now it's like this, that we are expanding our envelope up. More and more scrub here. The more scrub there, the hotter it gets here. And I can guarantee you this is getting hotter. And the hotter it gets here, believe it or not, the colder it gets here. You say, well, why would that happen? Hotter it gets here, colder it gets here. Colder it gets here, hotter it gets here. Everything's dipoles. This is all negative particles. These are all negatives. These are ions, ions, ions. Ions means negative. It's a negative ion. These are all negative particles. And right below is the dipole effect, because you got to have positives when you have negatives. And it goes down to minus 80 degrees Celsius. So you're above at 1500 degrees Celsius. That's like 2700 degrees-ish Fahrenheit. And this is about 112 degrees negative Fahrenheit. It's between this little border here. Now, then it gets hot again. All right, so the colder it gets here, the hotter it gets here. And then eventually it goes right into the Earth, because the Earth is ground. The Earth wants these electrons to come down, and the Earth will suck every single one of them in. So if the lightning comes down like this and you're in the way between the lightning and the ground, it'll go right through you and explode you to get to the ground. All electrons want to be in this ground. All of them want to hit the ground. All of them coming through here. However, as they come through, they're interfered with by ozone, by other particles, by solar panels, by, a guy's face, whatever. But they eventually want to get to the Earth. This layer right here becomes hot. And this layer here is becoming more compressed. everything's becoming more compressed. That's why we're getting so much turbulence. And then this, because of the compression, we're going to get more rain in areas where we didn't normally have a lot of rain, because the atmosphere is going to be compressed, and then you're going to get a lot of rain. Then additionally, because it's getting colder and colder, you're going to get big chunks of ice. And all that stuff falls down into this area, and then the heat just keeps building. Now, it will discharge into the ground, because the ground will absorb those electrons. Those electrons are heat. Those electrons are heat. So what will happen to the surface of the Earth? The waters will get warmer, which they are. The soils will get warmer, which they are. Everything is warming up and getting drier, which it is. And of course, there is areas of extreme precipitation. But this is what we're dealing with. Global warming is this scrub. It has nothing to do with carbon dioxide. Well, it has to do with carbon dioxide. It has nothing to do with carbon per se. You can't grab that carbon and say, okay, I got the carbon, no problem, we're all set. No. Once you expand that carbon into a gas, you're done. The carbon is what sequestered the oxygen. All right, in the ground, carbon has all of that stuff, hydrocarbons and so forth in the ground. Once you take them out, the hydrocarbons burn, and then they expand. It's a little bit complicated web, but not too bad. It's just fully understood. It's too hot out here, 2,700 degrees. Just explain that to me. They cannot. Explain the corona. They cannot. Explain both of those things. I did. All right, clear your mind. Just clear your little mind. All right. What are we seeing here? We're seeing radiation. We know out here it's millions of degrees, and we know back where the sun is, it's, say, 10,000. Now, these S switchbacks, they're seeing these fields come out, and then they're getting shaped like an S. They're being twisted back towards the sun. Now, the reason for that is the impact into the oncoming particles. Now, I would like to see if they see these switchbacks on the, well, they're going to see it everywhere, because the sun, there is no dark side of the sun. Oh man, I'm telling you, sometimes my mind blows up. I'm thinking to myself, I wonder if they see the switchbacks on the dark side of the sun. Oh God. I gotta tell you, that's just hysterical. I can't believe what I said. The dark side of the sun. You're going to get a bunch of flat earth people now that are going to say, well, nobody knows, there's probably a dark side of the sun. Well, who knows? All right, this is from the space observatories, and they're trying to figure out what's going on with the climate and how are we going to mitigate these issues and so forth. Well, here's the issue. This is California. Now, we're coming into the sunlight. I believe the sunlight is coming here, illuminating this side more than this side. All right? So in other words, we're coming in here, and the sun is probably hitting right up in here somewhere. I'm just taking it for, that's just a shot in the dark. But I do find it interesting that that looks to me kind of energetic. And this has a similar signature on the other side of there, but it's just diminutive. It has no real, energy to speak of. And you see how this is kind of bright looking, and this is not quite so bright looking. But it is our atmosphere. This is the atmosphere. When this atmosphere here scrubs through this atmosphere out here, and that is an atmosphere. I don't care what anybody says. Fermilab says empty spaces, and it is. There's no question whatsoever. All you got to do is look at these pictures they're taking. Say, oh, look at all this stuff, and we're about a trillion miles away. They have no idea where we are, because it's not homogeneous, first of all, so you couldn't gauge it by anything. And it's going to slow the stuff down, no question whatsoever. They're judging everything on the speed of light, and the speed of light is not one speed. It's just absolutely not. I showed it speeding up. We can speed it up easily. We can slow it down easily. You can speed it up. That means, you can slow it down. They always know that. But they say, well, that's because it's not in a vacuum. Well, I don't care. I can speed it up, not in a vacuum. That they cannot accept. That's why they won't talk to me. You got to understand dipole electron flood theory. There it is right here. This is acceleration of light. Here's how it started out. Here, which is the particle is in here and it has a big field around it. So the particle is tiny. A little tiny thing inside there, but it's a magnetic field. So everything around it is influenced. You take a magnet and you push it next to something, you can feel quite a distance away. This is what happens. It's coming through the air. Everything in the air has magnetic fields too, because every particle that exists is made out of the same things as light. They're all made out of these two particles. When you put them together, they're black and white, and here it is right here. This is that's what light is made out of. Those two black and white particles, here and here. Now, half of that is what you would really call an electron, and that's heat and electricity. But when you put two together, it becomes a photon, and that's light. Now, here it was with a field surrounding it, coming forward, pushing everybody out of the way, so they glow a little bit, this thing glows a lot, and then we put a venturi out here, which restricts the light and forces it to accelerate. That's acceleration. If you can't see that as acceleration, then you got a problem with your eyeballs. That is not my issue. If you cannot understand that is acceleration, nobody in their right mind cannot see that. That is the acceleration of the particle, which you didn't see before. You couldn't see it because it wasn't accelerated. Now it has accelerated and completely removed itself from the wave, and now it's extremely energetic and exploded. And all of the other fields that weren't even seen are now highlighted because they're being pushed back against. This one is highlighted because it's being pulled forward, but not much. These are being concussed like literally a subatomic bomb. That's exactly what it is. It's a subatomic bomb. These are the particles that explode and break apart into a subatomic bomb. Okay, my friends, the simplest atom that exists and the smallest atom is the hydrogen. And they say it has one big gigantic proton, and then, which is positive, and then one little tiny electron about 2,000 times smaller that is negative. And that's what hydrogen is. I totally disagree. I say hydrogen, instead of being this and one little tiny ball, this and positive and negative, it's the same charge, but one of them's gigantic and one of them's tiny. No, absolutely not. Throw that away. This is what it is. This has 18 and 25 or so dipoles. Each one of these is a magnet. Each one is a magnet. All right, and they glue together, and at a certain point, and it appears to be 1823, I'm thinking, is a proton. Now, you got to have a little additional charge for an electron. A proton is like a charged particle, and it wants to attract something. We want an electron to have an extra charge. I believe it could go both ways. I'm still working on this, but I'm going to tell you right now, it is 1823 or 1825. So I'm going right now with 1825 for the hydrogen, 1823 for a proton. But when you get a hydrogen, you're up a little higher, so you got a little extra energy there with that extra particle. And a proton is a little less. But it's certainly not this. Absolutely not. So this, no. This, yes. And 1823, and somebody said, well, how do you come up to 1823? Well, according to Millikan's oil drop experiment, he took oil drops and he measured them somehow. I can't remember how. This goes back 60 years ago. And he measured the weights. And he found it changed all kind of different weights, but it was the same change in multiples. In other words, it was 0.0005845 atomic mass units, and you could divide it. Maybe 10 of them changed this time, maybe 5 of them the next time. It was always a multiple of that number. So he surmised, which I agree with, he was breaking them up into different electron level amounts of electrons, basically. And so an electron weighs 0.00058 18.45 atomic mass units, and you multiply that times 1823, you end up with 1 atomic mass unit. That's how I came up with it. Now, is it right? I don't know. And 1823, I believe that's how I got it. Well, I know I got it that way, but I can't remember if that's the exact numbers or not. But it's that. It's 1823 was my number. And it turned out to be an extremely interesting number in a place called Strong's. But anyway, that's the hydrogen atom is the tiniest. It's the tiniest. But for me, it's not just 1. It's 1825 or so. And then you get up to helium. Instead of having 2 protons and 2 neutrons, you've got 4 times almost 2,000. You got 7,350, I think, something like that. 7,000 instead of 4. And as they get up here, you got bazillions and zillions and zillions. Because for every neutron, you're going to add 1824. For every proton, you're going to change it to 1823. So the periodic table has to change a little bit. And then we also have to take into account enzymatic functions and catalysts with the isotopes and the half-lives, because that's how the body works, is nucleosynthesis and nucleophilic substitution. And what I mean by that is catalysts can take these metals, anything they want. They can come in there and go and reconvert it just like that into anything they want. They can move it up the periodic table or move it down. It's the decay. The decay daughter doesn't mean it always goes down. It can go up. I've shown that extremely clearly. All you got to do is look up isotopes, and you'll see there's going to be smaller isotopes, and then you're going to get to a stable, and then you're going to have bigger isotopes, and then you're going to see the daughter isotopes can move up the periodic table. They don't have to move down. Decay does not always go down. With isotopes, they can go chop it up, put it back together anywhere they want. That's what an enzyme does. Okay, so everything we're talking about here is particles that are in space and on the Earth and in the skies and on Mars and coming off the sun. I'm going to tell you something right now. As far as I can determine, there is nothing that exists that is not made from these 2 particles, the black and the white. And as far as I'm concerned, they all come somehow from life. Okay, I know it sounds kind of crazy. I start talking about bacteria and about life and all that, and I always end up with electrons. Every single thing there is made of these 2 particles. I don't care if it's your eyeball, your teeth, or a bug. There's nothing that exists that is not made of these 2 particles. Everything there is. So, speaking about life, speaking about Mars, speaking about the sun, speaking about the corona, is also speaking about those 2 particles. This is dipole electron flood theory. Until we can get to understand dipole electron flood theory, there's no understanding anything. Nothing is correct. There is nothing that can become correct starting from incorrectness. They don't understand what's below an atom. Now, above atoms is a different story. Below atoms, no. And this is where energy exists. This is where we have to understand energy, enzymes, bacteria. These are inside of the nucleophilic and a nucleosynthesis. That's where we get our most, that's where everything really happens, inside of atoms. We don't even know where 95% of the universe is. It's inside of every atom we look at. We never see it because it's inside. It's completely coated with things that will bounce back at us. So that's it for today. Thank you. I love you all.